Okay, should be live. All right, there we go. Sorry about that. I am live now. Welcome everyone to World Quant Unit 2 Office Hours. Hope everyone is doing a fine day. I am back for the duration. Hope y'all were taken care of by Ross. And I believe he finished Q5 of the ML mini project. I believe he has wrapped that up and he's done with that mini project. So before we proceed, any holdovers from that mini project that people would like to bring up now before we continue on the next mini project? All right, I see Suleiman is here. Welcome, Suleiman. All right, I see Ramsey is here. Welcome, Ramsey. Anything people like to bring up about the ML mini project before we move on? I believe Russ has wrapped that up for y'all. Because if not, we can continue on with the next mini project. Okay, please, what's the distinction between PCA and truncated SVD? I think these are one of the things that aren't named so well, in my opinion. So there's often confusion between them. It says, I see Radot here, so I do want to clarify that, Suleiman. I see Radot. 9 and 12, 9 and 11 have yet to be loaded. So I will talk to Russ. So he can upload those office hours, or I could probably even do it myself. I can perhaps even do it myself and download those videos. So I will make sure I do that. Or if not, Russ will take care of that tomorrow. I see Abu Bakr. Welcome, Abu Bakr. I see Bongo. Welcome, Bongo, to office hours. And there's a question about the truncated SVD and the PCA. So let's explore that. It is a good question. I think it's one of those things that unfortunately gets kind of muddled by the names. So I very much do think it's worth considering what the difference between these are. Office hours today is October the 14th. Office hours 12, and that's the date. I think that's how I usually name things. Yep, and the same way I name things. All right, so I need a data set to play around with, and typically when I need a data set to play around with, I fetch that California housing data set. So I'll go ahead and run that, and I will say data equals fetch California data, and x equals data, y equals data, and target. And as always, we'll do a customary train test split. sklearn, model selection, import train test split. And I will perform the train test split right here. Okay, did my train test split. So let's consider our workflow. What I want to do is I want to have, here comes my data, and I want to apply some dimensionality reduction. I'll call that DR. And then I will give it to my predictor. Right there. And of course, in order for me to properly do dimensionality reduction, I need to scale my data. So from sklearn, pre-processing, import my standard scaler. And from sklearn, I think it's called decomposition, import PCA and truncated SVD. And from sklearn, I'm going to import Let's see, import, let me just say linear model and import, let's say ridge. Imported things I'll be playing around with there. So PCA is a dimension, both the PCA and truncated SVD are dimensionality reduction techniques. So for example, if I have a data set of two features, x1 and x2, don't view this as y and x1. Don't view that these are labels. Simply view them as two features, two dimensions, how our data exists in a two-dimensional space. And we might have observations that look the following. This way. So notice how these two features are highly correlated. And if two features are highly correlated, well, there's some redundancy. You can view this as redundancy in the data. If I have two features that are correlated or highly correlated, well, that means that I can get away with just using one. And get away with just using one or one new feature to describe the data. Let me better phrase that. If we have two features that are correlated with each other, there's probably a new feature I can derive that can still explain a lot of that information. So for example, that new feature probably runs along this direction. And there's a second feature that is orthogonal to the first. So instead of explaining our data using x1 and x2, these coordinates, we can then explain the data in a different coordinate space. I'll call that v1 and v2. And these coordinates are chosen in such a way that I can just use v1 and still explain a lot of the variability in my data set. So what PCA does, PCA takes a data set and transforms it into this new space. In which a truncated set of those features should be sufficient enough to describe my data set. That's what PCA is doing. Mechanically, what we need to do is we need to center the data set and rotate it. What we mean by center the data is that we make sure that each feature has zero mean. We need to center the data, have it centered so that each column has zero mean. In fact, we can take a look at the documentation of PCA. And let's go ahead and see what it says. And it says, notice the class does not support sparse input. We'll keep that in mind. I'm trying to look to where it says talks about this idea of centering. Let's see if it has that information there. I guess not, but we can go ahead and see what would happen. I guess I couldn't find it. Should expect it says something about it's going to center the data. The input data is centered but not scaled for each feature before applying the SVD. So we see here, we see some mention about PCA and we see some mention about singular value decomposition. So it's a little confusing. I'm not going to lie. I think they probably did a poor job of naming these things. Because in the algorithm for PCA, the first step, what's happening internally, is you center the data. You center the data. Actually, perhaps write that out on the notebook here. So the first step of PCA, center the data. So each feature has zero mean. That's what it means to center the data. Put it in the center. Each feature has zero mean. The second step of PCA is apply singular value decomposition. Essentially, it's running an algorithm to take the matrix and decompose it and find these dominant features, find these dominant new modes. That's that step of applying singular value decomposition. It's a two-step process. In fact, there are various algorithms one can deploy to calculate the new features. Think of PCA as an overall algorithm, how to find the a new set of features that are linearly related to each other and are orthogonal. That's the goal of PCA. Give me new features that are linearly dependent on my old features that are orthogonal. That's the goal of PCA. However, there are several ways to go about applying PCA, and one of the most common, most popular versions of applying PCA is you center the data and you apply singular value decomposition. There are other approaches. You can center the data. You can then calculate the covariance matrix. So this is another algorithm, another implementation of PCA is you center the data, and then next you calculate the covariance matrix, and you solve for the eigen vectors of that covariance matrix. So there's more than one way to implement PCA. There's more than one way algorithm to calculate PCA, to calculate those principal component, to apply that principal component analysis. They both should get you the same answer, but typically this approach here has been shown to be more efficient and faster, so it's preferred. So underneath the hood, scikit-learn is going to implement this algorithm here to calculate those principal components. Any questions up to this point here before we go into truncated SVD? Okay, do let me know if there's any questions right now, but I'm going to recap. PCA, a way to reduce dimensions of my data. What's happening, the actual algorithm implemented by scikit-learn is you center the data, zero mean for each feature, and you apply singular value decomposition. Now imagine, well actually, let's see if I can, let's see. No, I think it adds back to mean. So let me try it out. Let's try it out, right? Let's try it out. So I can say PCA equals PCA, and I would choose how many components? How many components I need to achieve 95% variability. I can say X of t, the transform version. I can call fit in transform on X train. And all right, looks like it only needs, because I didn't scale my data. I did not scale my data. So that's why I only found one feature. So I can probably put this in a pipeline from sklearn. Pipeline, import pipeline. So I say pipe, pipeline, and I have my scalar, or standard scalar. Actually, I'm going to use a min-max scalar. I'm going to use a min-max scalar. Pre-processing. The reason I'm doing it is because I want to avoid using a transformer that's going to center my data. I think, in fact, let me double check standard scalar. I believe there's a way in standard scalar to not center it with mean to false. I'll do that. I would still use my standard scalar, but I would say with mean equals false. So in other words, I'm not going to subtract by the mean. I'll just divide by the standard deviation. And now if I look at X of t, let's see how many features I have there. Still have one feature. Oh, because I'm doing that instead. All right, let me just finish this pipeline. And then I have my dim reduction, PCA, and components 0.95. So let's try this out. Call fit in transform on X train. have 6 features. Let me recap because I know I do type fast and I want to make sure things work before I really explain what's going on. So here a pipeline is going to scale my data without using the mean, So I simply divide by the standard deviation, and I said, let's do PCA. Give me the number of components I need to achieve 95% variability, which apparently is 6 features. Now, keep in mind that what's happening underneath the hood is that PCA accepts the data that came in, and the first thing it does internally, it centers the data. In fact, if I look at my pipeline and I say, give me step 1, let me look at some of those attributes. Let's look at call dir to see available attributes. And let's see what I am interested in. I'm interested in the mean underscore. Look at that, mean underscore. Let's look at that, mean underscore. And since it ends in underscore, we know that's only something we know after we fit the model, after we've fitted the model. And there is the mean of each of my features. Let's go ahead and make sense of it. If I take my pipeline and I say, well, let's just call transform on the first step. Well, there's my data, and if I calculate the mean, if I want to calculate the mean for every column down the rows, that's axis equals 0. And we get the same numbers. So what I'm trying to show you here is that if we give it a data set that has not been centered, the PCA algorithm in scikit-learn, it will center the data. Centers data, then applies SVD to come up with the new components. Questions right now before we dive into, look at the truncated SVD and see the effect of that. Okay. So imagine you have a sparse matrix. A sparse matrix is one where there's a lot of zeros in the data. So there are more efficient ways to store a sparse matrix in memory as opposed to the traditional ways. In a traditional array, you store every single value in memory. However, if you have a lot of zeros, wouldn't it be more memory efficient that I only remember the locations of non-zero values? Wouldn't it be more efficient if I have a lot of zeros, I only remember the location of those non-zero values? So there's 2 pieces of information I'm going to learn, or I'm going to keep track of, keep in memory for this new approach. And that is the value, the actual value, and its position, what row and column it's at. So we can kind of view the row and column as an integer, whatever many bytes we're storing for that integer, those 2 integers, and the actual value. Keep that in contrast with actually storing all the zeros in memory. How much more memory intensive it is. So a sparse matrix. Hey, there's a lot of zeros out there. Do I need to memorize where they all are? No, I'm only going to keep track of where the non-zero values occur and their respective value. Great, that's a sparse matrix. Great to work with. I see a question here is, for your explanation, centering the data is mean 0, but here we have values for the mean. Oh, so keep in mind that PCA centers the data. This here is the output after scaling, which we did not center. So kind of recap here, here's a scalar, but since we said with mean false, it doesn't center it. So the data that comes into the PCA, that second step of my pipeline, needs to be centered. And we proved it to ourselves Because we look at pipe 1 and we realize that it has a mean. This is this right here is the means of the data that came into the PCA. And this is the mean of the data after scaling and I guess I could have said and before being fed into PCA. Yeah, so I'm showing you there that we did not center the data, so PCA did it for us. So there it is. There's proof that PCA had to center data for us. Because if data was already centered, this would be 0. These would be a 0 array. So now let's prove it to ourselves. What would happen if I center the data? So now I'm going to say, more precisely, now let's have our scalar center the data. So I'm going to say with mean true, just to be explicit, which is the default, but I'm going to be explicit. I'm going to say pipe, scalar no center. And now if I say pipe scalar no center fit on X train, and then now let's repeat the process. Let's look at the mean of my PCA. Oh, look at that. Look at that. They're all nearly 0. Strictly speaking, they're not 0, right? They're 1 times 10 to the negative 14, negative 18. So it's within machine learning error, right? It's within machine precision. Put a comment here and say, these are the column means for the data when we did center the data before the PCA step, right? 1 times 10 to the negative 14 is nearly 0 and within machine precision. So in fact, if we look at what it is after the scaling step, which we did now center. Let me just change the name here to scalar no center. And it's nearly 0. It's the exact same answers, right? Exact same answers. So to recap here is what we proved is that when we use PCA in scikit-learn, it's going to scale the data. It's going to, center the data. I said scale, sorry about that. It's going to center the data. Even if the data is already centered, well, we'll try to center it regardless. It's because that's just a requirement in the algorithm, in the implementation of PCA that it needs to do. It needs to center the data. If we give it data that has not been centered, it will center it for us. If we give data that has been centered, it will try to center it even further. So hopefully, Sahid, that answers your question. But do let me know. Do let me know if anyone else has follow-ups, additional questions right now before we transition to truncated SVD. Okay. All right. Do let me know if you come up with any questions. But now let's go back to truncated SVD. We discussed how if we have a sparse data set, we're going to only store the location non-zero values. Now imagine what were to happen if I take a sparse data set, one in which I'm storing it in memory as a sparse matrix. Only memorize the non-zero values and their location. What were to happen if I were to center a sparse matrix? What were to happen if I were to center a sparse matrix? In fact, let me try to create a sparse matrix. And I would say, give me a NumPy array that is nothing but zeros. That's 100 by 5. And I will change a couple of those values to be something else. Besides 0. Get an index error. Let me just, oh yeah, of course, because only 5 columns. 2 and 4. So I have this matrix, this NumPy array, and I'm going to convert it to a sparse matrix. And let's see if I know how to do that. I guess it's not called sparse. I think it's in SciPy. From SciPy, import. In fact, since I rarely do the conversion myself, I'll probably Google it. Convert NumPy array to sparse matrix. See this question, this answer from literally 10 years ago. All right, I guess the function is called sparse, or the module is called sparse. Import sparse. I can say from the scikit-learn sparse, import let's see, SCR matrix. Oh, there he goes. SCR matrix. There are various ways we can create sparse matrices underneath the hood. Let's not get into that. But there are various ways to go about various variations of this sparse idea. How it's best implemented. And now I have my sparse matrix. Right, it tells me that it's 100 by 5, and I'm storing 3 elements. Which makes sense because there's only 3 non-zero values. So in fact, I can probably do something like import get size of, import sys from sys, import sys. I can say sys get size of. Let's do this before and after, right? I'll call this full. I'll call this full. We'll make some changes here. Call that full, and I'll call this full as well, or I'll make sure I change that to full. So I have 2 NumPy arrays, or 2 arrays. I have one that's a full representation, and one that's a sparse representation. The sparse representation takes up 48 bytes. Let's see, get size of, and this should tell me bytes. Okay, just make sure it's in bytes and not bits. Figured it's in bytes, but just want to make sure. Let's look at the full representation. So notice how the full representation takes up 4,000 bytes. We can kind of rationalize that. Let's try to actually calculate that, why that's the case. I can look at the D type, and I have a float 64. So in other words, I have 64 bits. There are 8 bits per byte. And how many numbers I have? Well, I have 100 by 5. I can do that a little more precisely, more programmatically, by saying, let's look at the shape and multiply that together. It's 4,000 bytes. It's a little more than what get size of returns because we're probably storing some additional information about the array. But notice how a bulk of it, we can explain. We did the math and we explained that this array should be at least 4,000 bytes. We probably chosen a bigger array and we realized that this little offset not going to change so much, but we have a 4,000 byte NumPy array. Well, here it's 48. It's 48 bytes. Let's also try to rationalize that, right? Let's try to go and try to rationalize that. We have 3 non-zero values. Each non-zero value takes up, it's a NumPy 64, so it takes up 64 divided by 8 times 3. Times 3, and we're going to plus, right, that's how much 24 bytes the numbers take space of. And we are going to add the locations. The locations also take 8 bytes. So we get 48. We're able to explain where we got our number from. You didn't understand how I came up with those numbers? That's fine. That's okay. But so I'll recap that there. Since each element takes up 8 bytes, I multiply by how many elements I have. 4,000. This is a function in Python to get how much things takes up in memory, and it's pretty close to my calculation. This here, I'm only storing the non-zero coordinates and the actual non-zero values. So notice that, 48. Now my question to you is, what would happen if I were to center that data set? I were to center my sparse matrix. What will happen, you think? Okay. Yeah, what would happen if I were to take a sparse matrix, invert it, and center it? Any idea? Any guesses? What would happen if I were to... What were to happen if I try to center a sparse matrix? I see a question here. I see it will pop up value error. I'm not looking for necessarily an error in Python. That might happen, very much might happen in Python. Actually, I don't know what would happen if we try to programmatically try to center it. There might be, well, we'll see it play it out, but lose some information. We're not going to really lose information so long as we keep the mean. We can always do the inverse transformation. But let's try it out. Thank you for your answers. Let's try it out. Get a non-implement error. Subtracting a non-zero scalar with a sparse matrix is not supported. Okay, well, what if I try to say sparse, and I say mean of every column, and I subtract it? Well, it actually worked out. It actually gave us an answer. It did a response. It actually did something. And I'll call this x sparse centered. It actually performed an operation. But notice, then if I say, well, let's check out how much memory it takes up now, because it doesn't look like a sparse matrix anymore. It's 120 bytes. So it definitely blew up in size. Nothing too drastic. I'm a little surprised it didn't blow up too much, but it did increase in size. Now let's consider what would happen if I were to get size of on the X full, and let's center that. And that was the same amount. Notice what happened here. If I tried, I think I know, let me if I subtract it by a different value. Let's do that instead. No, I subtract by the mean. Okay. Notice how if I center the full representation, a NumPy array, the file, the memory object stays the same amount of size. Doesn't change. 4012, 112, 4112. But the sparse matrix, its file size, not file size, its memory size took up. Its variable size, how much it takes of memory, increased. Now it doesn't, the increase wasn't so drastic, right? It went from 48 to 128, right? 80 bytes, 80 byte increase. So what, right? 80 bytes, so what? But imagine if I had a big data set. A big data set in which a full representation I was not able to hold in memory. So it looks like if I have a big data set that is impossible to hold in memory, but it's only possible if I have a sparse representation, then centering the data, I can put a little comment here, centering the data, centering a sparse matrix increases the size of the object. Thus, for really big data, we run the risk of not having enough memory to represent the resulting centered data. So now we have a problem. Now we have a problem that we cannot, that we run the risk of running out of memory if we try to center a sparse matrix. We didn't have that issue when it was only 100 by 5, but we're definitely going to have that issue once we get something that is bigger. Actually, I want to play around with something here. Let's see if I can get a more drastic effect. Let's actually say x full 5 and change 1 to be -1. And let's change 3 to be 48. Let's see this effect as well. Still the same. Still say the same. But nonetheless, you can imagine how much more of an increase it would get if we had a bigger array. Questions people have before we kind of connect this with truncated SVD. Where does that come into play? And the ramifications of this problem here. Okay, so because centering a sparse matrix runs the risk of crashing your program running out of memory, in scikit-learn they're probably not going to let us try to center a sparse matrix. In fact, you might get a value error. You might get an error raised saying, hey, I'm not going to let you center a sparse matrix because it'd rather raise an error than crash your system. Right? As we saw here, yeah, I could center a sparse matrix, but that might crash my system. So scikit-learn probably takes the approach, if we try to give it a sparse matrix, it will actually raise a value ever. I don't know. Let's try that out. I don't know, so let's try it out. Pipe, and let me do copy, because I don't want to change the original. And fit transform on x sparse. Pipe has no copy. Let's see there. I think it's called clone. How about this? I want to clone my transformer. I don't want to mutate the original one. I want to create a copy. So I, from scikit-learn utils, import clone, I believe. Let's see, scikit-learn clone. Base clone. Okay, would not have figured that out. It's doing something. It's doing something. So an error hasn't been raised yet. I thought an error would have been raised, but it's taken a long time. All right, so there might be an issue. So we might run, or we have issues if we try to apply PCA on a sparse matrix. We may get an error, take forever, or crash our system. In fact, I'm going to close this off here because this is going to keep on going perhaps. So I have an issue. I cannot apply PCA because it requires centering my data on a sparse matrix. So this is problematic. This is problematic. So what I'm going to do here is, or the solution to this here, right, the solution to this problem is to use a variation of PCA. One in which we don't center the data prior to applying SVD. So if the problem is that we can't center the data when we apply PCA, why don't we just apply a variation of PCA? One in which is not going to center the data initially. So it's the same steps of PCA. It's just that we skip the centering part. Strictly speaking, this is no longer PCA. Right? Strictly speaking, mathematically, you're not applying principal component analysis. Strictly speaking, you no longer apply PCA because, strictly speaking, PCA requires centering the data. So, what do we call this other transformer, this variation of PCA? So, since it's not strictly speaking PCA, what should we call it? Well, they have confusingly called it truncated SVD. So let's look at the documentation, right? Let's kind of prove it to ourselves. Look at the documentation. Dimensionality reduction using truncated SVD, aka LSA. Treasuring performs linear dimensionality reduction by means of truncated singular value decomposition. Contrary to PCA, this estimator does not center data before computing the singular value decomposition. This means it can work with sparse matrices efficiently. All right. It's good to hear. Good to hear. So out of completeness, we will implement this. So I say pipe truncated. And I'm going to scale my data. So my scalar, standard scalar. Got to make sure I say with mean false. And then I have my dimrud. And notice how you may have seen sort of my style of how I call my steps. I avoid calling my steps variations of the transformer used. Some people like to say standard scalar equals standard scalar. They like to say PCA equals PCA. They like to say linear regression is equal to linear regression. I avoid that. I actually like to name my steps a little more generic because it's more like, okay, I'm using a scalar. What kind? Standard scalar. I'm sort of acknowledging that I could use a different type of scaling. I could use a different type of dimensionality reduction. I can use a different type of regressor. In fact, I'll show you exactly what I'm talking about. Truncated SVD, and say n components, let's say 6. And now I can say pipe truncated fit and transform X train. And I get a error because it's called X train, not X tryon. And there it is. There is my transform data. So let's just show you a comparison of what I'm talking about, the style of I name things, just so you can know what I'm talking about. I could have named this standard scalar. I could have named this truncated SVD. I can even have a predictor and called it, tree, and have a decision tree regressor. Compare this with this, where I said it's same. Okay, it's a scalar step. What's kappa scalar? Well, you can look it up, but I'm acknowledging that it can be a different scalar. What type of dimensionality reduction? Well, it's a SVD. Let's not say tree. Let's generically say regressor. I'm just letting you know my style. It's a little different. And since I don't want this to run, I will comment it out, and I will comment this out right here. Okay. Questions people have? Nearly the full hour on truncated SVD and PCA, but I think it's a rather confusing topic. So the moral of the story is, if I have a sparse matrix, I cannot center it, so I cannot apply PCA. So instead I apply truncated SVD, a variation of PCA that strictly speaking isn't PCA, but gets away with not centering the data. Okay, let me know if there's any follow-ups, additional things people would like to bring up. Floor is open. Any questions about what we just saw or what we just been working on? Okay. All right. Okay, all right. I think we cooked up a nice little notebook about truncated SVD versus PCA in this hour here. All right. Let's see. What are other things we wanted to talk about and discuss for our last 10 minutes of Office? I think it's a little too late to crack up the NLP. I think cracking up the NLP mini project starting off next week is sort of a good way to kick off week 4. I think we want to talk about bring up right now. We have about 10 minutes left. And by the way, I have uploaded videos 9 and 11. I have uploaded them to the shared drive. There they are. So go ahead and have fun. Parameters for truncated SVD other than in-component still important? Good question, Renato, because one of the things I try to stress is when we learn these models, when we learn these estimators, we ask ourselves, what are the hyperparameters? And more importantly, what are those key hyperparameters? If we're in truncated SVD, it's probably just going to be n components. It's just going to be n components. However, I'm going to take a look at the documentation just to make sure there's not something, oh yeah, don't forget about that. And I'm looking at this, and really, it's end components. It's end components that you should be playing around with. Keep in mind that random state is, you can kind of view as, it's strictly speaking not really a hyperparameter, but it's something that you should always set. One of the things that I want to stress as well is when we learn about these models, we should ask ourselves, is this a model that relies on randomness? Is some sort of random process invoked? Because we want to make sure that the work we do is reproducible. So any of these models, we need to set the random state. Any of these models that have randomness, by the way, only those that have randomness, not all those have randomness, will have a random state attribute that should be set so you have repredictable results. In fact, I didn't do that here, so I'm going to go back and make that fix just out of good habit. Since it's a model that relies on randomness, I should set a random seed. Doesn't matter what the integer we choose, just make sure it's consistent for that object. I'm going to do that. I'm going to put also here, like I said, just good practice. So thank you, Renato, for bringing up that question. It's a good question to ask. And now you have made me realize that I should have set the random state for SVD. I guess it requires a random algorithm, maybe to figure out the best starting point, the best initial values. So strictly speaking, we're going to set random state so we can have reproducible results. Thank you for that. I see Suleiman has a question. Is it really necessary to scale a dataset before running random forest regression? No. Random forest is a model that does not need scaling. Strictly speaking, does not need scaling. In fact, its results are invariant with scaling. In other words, whether you scale or you don't will not affect the random forest or decision trees performance. Any type of tree-based model, whether you scale it or you don't, has no effect. Good question, good question. However, because it has really literally no effect, people tend to still have it in their workflow because it makes it very easy for one to switch out models, right? If we have my workflow, let's say I do my workflow here, and I do something like, I have a process that's, polynomial features and scale, and then my regressor. And if they try different regressors, like, oh, let's try, random forest, let's try gradient boosting, let's try SVM, let's try nearest neighbors, it's very easy for people to just keep the same workflow where it already has a scaling step, right? It's being a little lazy. It doesn't matter if we scale or not, so it has no effect on the tree. I don't want to have to modify my pipeline because later on I might use SVM that does need scaling. So yes, exactly, Suleiman, but you'll often see people included in the workflow because it makes it easier to try out a different model if that model requires a scaling, and most models that we've seen so far do require scaling. All right, good question there. We got about 5 minutes left. Anything else we want to bring up with our time here before we end for the week? I know there was asked a question about nested grid search. I've been busy this week, been out here and there, so I haven't had time to properly look at that article, but that's on my to-do list, so I could properly understand what's happening with nested grid search, so I can report back to you and explain it to y'all. Anything else we want to bring up? Right, we got a couple of minutes left for Unit 2 officers. Things we want to bring up before we conclude. Well, if there are no other questions, last call before we end a couple minutes early. All right, I'm going to end a couple minutes early Looking forward to next week. Crack open a new mini project. Take care, everyone. Have a good rest of your Thursday. Have a good Friday. Have a good weekend. And see you back on Monday.